Okay, as I mentioned in the first class, I want to make this class not passive mode, but rather the active mode. In other words, the way I usually assign the homework is like a passive mode, because I have given all the information. It's analysis mode. Then you compute for the one solution. But I changed my mind starting this fall. I want to change it to active mode. In other words, you generate the model, then you, in your area, in your thesis area, especially thesis research area, you develop the model, then you estimate whatever I ask for it, then I'll select maybe 2 to 3, the model, and we can learn all together. Okay, that's what I want to do. I call that as active mode rather than passive. Passive, you go just a none. Okay, here is the answer, but you develop the answer yourself. I'm going to assign the one homework. I don't want to give you, nice printout, but I'll just talk. Then you develop the probabilistic model. So then you can turn in like before end of next Wednesday. So about a week should be good enough. Okay. Well, sometimes if you have some urgent problems, emergency problem, you talk to me. It can be delayed. You can just hand in any time earlier. That's fine also. Okay. In graduate study, I want you to have really initiative to do any assignment. Okay. So that's all I care. So the last Monday, I started to talk about the probability density function. Of course, most of you took the course on the statistics and the probability, but this time, this is really for application and to get the motivation to connect into your research mode. And I talk about the normal distribution, or it is called the Gaussian distributions. Very typical, very standard, the probability density functions. Okay? And of course, I'm going to talk about the properties of a probabilistic model. But in your area of the research or in your area of interest, develop the Gaussian probability density function. Okay? In your area of the research, I want to really know and try to help you. You develop the model. How to develop the model? You have to search for some database. You have to really look for the database, and you have to develop the property of Gaussian density function. Of course, you have to assign the x and y axis. Then then you have to plot it. Then you fit the curve. You may use any tool which is available to you. Okay, so it's not going to be all same. It's not going to be yield stress as I give you as example. Maybe something else. So that's what the interest is. Then so first, I limit. I don't have to limit, but in this class, at this time in the semester, I have to limit. So develop the normal distribution function, normal. So you're going to limit. Or this is sometimes called Gaussian probability density function. This is, I said, we'll call the PDF, okay? To do that, as I mentioned, you have to develop the database. You have to search for it. It is available. Lots of information is available. If you can find it through the internet, then you can just search for it. Then in the meantime, then you can learn what's available, in what forms, things like that. It could be simply like a histogram kind the database may be available, or XY data set may be available. So then after you got the, for example, histogram, then you have to get the continuous probability density function. Once you get that, of course, you would say, geez, what's the Gaussian density function form, equation form looks like? Of course, I'm going to teach you, show you. Most of you may know, but you have to look for it. If I didn't get to that point yet, that's the mode I want to operate. Then you can really think in conjunction with your work, because you all belong to the lab that your advisor is operating. Okay, so then it's still going up because it's a Wednesday. Maybe it's coming down on Friday. Then I want you to develop the mean. This is a symbol I'm going to use. You will see that today, of course. Mu x. X is a random variable. Something like yield stress. Could it be loading? Could it be ocean wave height? Things like that. Okay? Mu x. And I want you to compute the sigma x square. Sigma x square is so-called the variance. And some of you could say, geez, he's assigning the homework without telling us what that means is. Of course I'll tell you, but if I don't get there on time, then you have to look for it, right? That's the beauty. Excuse is this is graduate school. This is all basic material before we getting into the structure, the reliability problems, okay? And this is, of course, the variance. And sigma x squared. And sigma x is so-called, anybody knows? Sigma x is called, 중간? Say standard deviation. Everybody heard about the standard deviation. Okay. 진규? 진규, right? Standard deviation. I know you didn't take the probability course. That's why I'm asking you. In common sense, the standard deviation, what is it? What's good for it? When you get the data set, then compute the standard deviation. Well, how can I use that, the standard deviation? Or if you square it, that's called the variance. What's good for it? It's all basic material. You don't have to, I don't demand you must know. Anybody can tell? Kyung-suk, what's the standard deviation good for me when I get the test data, available test data in the ocean systems model? What's good for it? Youngyan, what's good for it? I love you because you always smile, but he married. What's good for it? Standard deviation. That's what we're going to learn. There's a measure of dispersion of the population of the given data set. Dispersion is high standard deviation. What does it mean? Is it good data or bad data? It's bad. Dispersion. Dispersion is a spread of the data set. Widespread, higher the variance or higher the standard deviation. About the what? The center. Dispersion about the center is about the mean. What does it mean? What's the mean? Gosh, she's asking all kind of the stupid things, But that's the basics of the probability, the data set analysis. Mean is a central tendency. Central tendency. What's about the middle of the curve? Yield stress, I exemplified last Monday. 36 kpsi, about 3,000 megapascal, which is about the center of the population. That's what you are telling. So measure of the central tendency. That's what you're looking for. Pick up your own data set, whatever that is, then compute the mean. Mean, sometimes probability content, they call the expected value. You don't have to write all this. I'm going to give you my handout. I was busy even yesterday to type in. Very condensed handout. That doesn't mean that, he said don't write. Well, you can keep writing, because by looking, by writing, by hearings, it's going to all helping the details of the problem set. And the sigma x square is a variance, and of course I'm going to show all the detail. And sigma x is standard deviation. And this is a basic given assumption. So you have to look for the case. It could fit nicely. It could be like this. If you have a positive or negative, the value in your data, or it could be something like it could be all like this, doesn't make any difference. Then this is upside down bell shape for normal distribution, beginning of the probability model. Then this is like mu x, okay? Then all the experimental data, sometimes, depend on the data set, doesn't go below 0. But normal distribution wise, this will go down and go down, will never touch the x-axis, horizontal axis, never touches. But getting infinitely close, okay? And in the positive direction is going to be infinitely close. Then the question is, do we have such a model to fit this probability in reality? My answer is no. However, for engineering computation, we can live with a few percent error. We don't much care way down the stream here, way down the stream, we don't much care. But majority is most important, okay? So, and it's a symmetric, very straightforward, symmetric. We're going to develop all the equation, symmetric, at about the middle, about the mu x. So there is no skewness for this model. For the typhoon, wind speed model is skewed for probability model is concerned. So we're going to learn that. Log normal distribution, Weibull distribution, Poisson's distribution is all skewed. Without application, just learning the model, no fun. So we're going to tie with some applications, okay? So that's what no skewness means third moment is equal to 0. I want you to keep hearing, even if it's strange. But when you hear it and keep hearing, when I talk, oh, that's what he mentioned. So simple. So that's the way I'm going to work on. Okay, probability density function, it relates to the reliability of the system. In this class, I'm dealing with the structural reliability, of course. Then it related to, as I mentioned, probability of the failure or the probability of the survivor, which is complement each other. So PF, I did already. I fully remember what I want to teach. Before I come into the class, I review what I should teach today. So I covered this last Monday. Probability of the failure plus probability of the survivor is equal to the 1. So your goal, target, objective is really to compute the one term or the other because it's complement each other. Let's say the probability of the failure. I haven't defined mathematically yet. Of course I will. So somebody could say, geez, he keeps saying, I will do it, I'll do it, but he talks, of course talks. Then when you conduct the deterministic design, you preset the yield stress, 36 kpsi, 36,000 pounds per square inches. Okay, yield stress. Then saying that by applying the actual loading, you want the related stresses in any location in the system should not be larger than the yield stress to avoid any possible permanent set. What does it mean, permanent set? You apply the loading, okay, then release the loading, then it's going to go back to original forms. If it's not, if there is a permanent set, then there's a permanent deformation occurs. That's not what we want in most machinery design. It wants to stay in the elastic region. Depend on the material. You could maintain such a phenomenal behavior, but sometimes you can. Aluminum. What's the yield stress for aluminum, Yonghyun? What's the rough range of yield stress for aluminum? Aluminum. Lots of ships, fast ships, they use aluminum nowadays. Aluminum is not a good material from the standpoint of maintaining the structure integrity because this is stresses. Steel, oops, is straight up, okay? Was like this. Aluminum doesn't do that. Aluminum, there is no yield. There is no yield. There is no linear region. Everything is degrading. Degrading and collapse. So here you don't use a lawnmower to cut the grass because you have a wonderful apartment living and dorm living, then you don't have to touch. But in the state, in US, every weekend I have to spend about 3 or 4 hours to mow the lawn, to cut the grass. Any lawnmower, it has a shaft, right? Shaft is subjected to the torsion. You will never discover the lawnmower whose shaft is made by aluminum. Why? There is no yielding. It degrades, and the fatigue failure is imminent, fast. Okay, so that's the main reason. There is no shaft. If somebody made by shaft by the aluminum, that's wrong design. If you find any shaft with whose cross section is like a square or rectangular or triangular, something wrong. That's wrong design. Why? Stress concentration problem. So it's always round to avoid the stress concentration, vice versa. So probability of failure is like a yield stress. You set the yield stress as a 36 kpsi. That's not like when you get the data set plotted, it could be right here is mu x. This 36 kpsi is not the mean value. Usual design, manual, if you look at it, is that you take the 3 sigma x or 2 sigma x, jack up higher, then set this guy as a design strength. I'm going to say R. R design. This could be something like a 36 kpsi. Then design against the given, the reset, the yield stress. Same thing, similar way in the reliability analysis or reliability-based design. Rather than setting this tolerable or allowable. This is like allowable. This is beginning of the class, usually first week. I just talk the directions, what's in the reliability, what's in the design idea. I'm going to really concentrate on design in conjunction with analysis. This is allowable. The resistance or strength, right? In the similar way, in the reliability-based design, I have to set the tolerable or allowable, same thing, tolerable. Tolerable. Is it correct? It looks so funny, but check. So for the probability of the failure, question is, what's a tolerable or allowable or, okay, probability of the failure? I'm designing my building, my ship, whatever, offshore structure. What's a tolerable or allowable probability of the failure? That's what design really needs, these informations. Allowable. So that's what I'm going to talk first. So based on so-called CIA code. This is in Elishikov, Isaac Elishikov book, around the page 25, 26. You can make a copy. I am not going to provide a copy of those. You can make a copy. It's around the page 25, the second reference book. You can look at a couple pages, you can look at it. I'm going to cover that particular Sharia code. This is developed in 1977. 1977. This Sharia really means the C is construction. Industry. Why? Industry. Research. Association. Information association. Info association. It's a long name. It's one of the organizations who developed the criteria for probable, allowable, tolerable probability of the failure. Then you have to compute all that. Then if it's different from the proposed, the allowable, then you have to recompute, the iterate process, vice versa. But this is not the absolute God, okay? If you have another backup material, of course, you can. Usual PF for structure system. Structure system, not the processing. Structure system by the rule of the thumb. Rule, that's the expression people are using in the state. Rule of the thumb. There is no written heavy backup, but that's the usual, the value we are working on it, vice versa. PF, usual, without any guideline, PF tolerable or allowable is usually 10 to the minus 5th to 10 to the minus 6th. What does it mean? What does it mean? When you compute that, then if your computed result tells 10 to the minus 5th or 10 to the minus 6th, that's a very good design. What does it mean? The chances that the structure system fail is very small, 10 to the minus 5th. But problem is, one out of many is bring the disaster, total disaster. Okay, it's not fixable usually, just breaks off. Machinery components done. The structure system is done. Probability of chances to fail is what the PF is. So if you don't have any particular information through the ship manual or ocean systems manual to build, or submarine or surface ship, basic guideline is 10 to the minus 5th or 10 to the minus 6th, usual, the rule of the thumb, okay? But this Syria propose particular the equation set. Okay, particular equation set is like this, proposed, okay, by Syria is equal to 10 to the minus 4 zeta s and t over L. I don't know the root where this particular equation came out, but this is good proposed, the kind of the tolerable. Tolerable means allowable. Okay, so and zeta S is called social impact factor. So it's called criterion factor, which is in the table. Range is from something like a 0.005 through something like a 5. Depend on the type of the structures. Okay? The range is something like a 0.005 through about the 5. Page 25, make a copy. Then there is a tables and all that. So something like a dam. Something like a dam kind of structure. So place of public assembly. So it's very small. If this guy is small, PF is getting small. Which means allowable failure probability is smaller. And some other structures, something like offices. Or industrial building. Industrial building is 0.05. It's a little bit higher. What does it mean? Allowable, the failure probabilities are a little bit higher than other. Tolerable. And bridges is 0.5. And towers, mast, etc. is higher. Higher means, what's the higher means in the denominator? The probability of failure goes up. Allowable PF slightly increasing. Okay. And what's the usual ocean plant? And Professor Chang's research area, FSPO? Is it correct? SFP? What does it mean? What's the full name on that? Louder.
Floating production.
What's the life span of that ship? 30 years? 40 years? 20 years?
I guess at least 25 years.
Yunso, you agree? 25 years. What does it mean? That plant has to survive. Has to survive 25 or 30 years, whatever it assigns. Then you need to do what? That system, structure system, has to be very stable for the next 30 years, right? Then you have to estimate, don't you? In the design process. Not only processing reliability is required, in addition, the structure reliability has to tell it will survive next 30 years, right? You have to prove it. Good design, bad design, you can start from, of course, component design. Reliability-based component design. Then you will estimate eventually the system, structure system design. And even if first week I talk just whatever I want to talk, okay? I just talk. Even if each component, okay, has a great, which means very low probability of the failure, that doesn't mean that the system, the structure system, is going to be very low probability. Answer is no. Depend on how you design the structure system. One component failure can induce the failure of total structure. Okay, which is called the weakest link structure. Weakest link structure. One component fail, then the whole system fail. Good design or bad design? Bad design, okay? But it could be economic design, but one component fail, one component fail, whole system fail. Weakest link structure. Another type of the structure is one component fail does not induce the failure of the total system, which is called the fail-safe structure system. Two different kinds. So this is a cost maybe a little bit higher, but it's a fail-safe system. One component fail does not induce the failure of the total system. So back to the allowable, this is a tolerable or allowable failure probability. T is design life of structure in years. T. And L is average number of people within, in the structure or nearby. In general, you could say the Elishkov book saying during the period of the risk, but you can just simply say average number of people which usually occupy the structures. Some office building, the World Trade Center that collapsed when the airplane hit it near the top of the building, that contains at least minimum between 7,000 to 10,000 people. Then 3,000 people lost their life. But so this is what very rough kind of the measure. There is no such a thing as exact. You want to live in the exact world. Our personality is always looking for the one number. Believe it or not, you are looking for one number. Then you are very happy. You will have a beautiful FEM model, very complex and all that. You are looking for the final answer, one number. Whether it's wrong or right, that's what you usually want, which is analysis mind. Design mind should be different. I want you to really develop into the design-oriented mind. Then you can really design your life beautifully and have a very satisfactory and comfortable life. As example, I want you to compute yourself. And as example, for example, zeta S, social impact factor is 0.5. So let's say rough range, 0.5, like a bridge design. Okay, bridge, I'm going to design the bridge. Then what would be the allowable probability of the failure, which I assign to compute? The zeta is, let's say, 0.5, and t is 30 years. Usual bridge design depends on the design types, all that. Of course, could be more than 30 years. Some bridges is there forever. Could be 100 years. So 30 years. And average number of people occupy that is, let's say, 10,000, 100,000 people. Then you can compute the tolerable PF, which is something like 150 10 to the minus 12 when I compute that. What does it mean? 10 to the minus 12 multiplied by 150. That's a tolerable the probability of failure. What does it mean? Your design factor for PF is no failure. You do not anticipate the failure. Okay? For the design. Probability of survivor is 0.9999999. Total survivor is what you're looking for. And for the probability of the failure for the life, our life, this Fukushima disaster, so many people killed by tsunami, by earthquake, all the combined effect. Usually when you deal with the probability of the failure for life, human life, you are dealing with roughly 10 to the minus third power, then you're okay. That's really for tolerable probability of the failure for life. Much lower. Okay, back to the basic probability theory. There's more. I could just list out the equation after equation, then hand off, but I don't want to do that. I don't want to do. Because I will be here another 2 years, at least 2 years, and I want to really talk some meaningful things for the young people like you. Then you can really contribute all the effort for better life. Korea, think about some years back. It's really wonderful environment for living is what you have. So keep improving. So that's the beauty. An Chol-soo is a fantastic person. He was going up and up and up, and I thought there is no limit in the sky for him, but he hit the concrete barrier yesterday. Then he said, "Oh, I'll quit everything. Back to school as a professor." Maybe that's the best resolution for him. But young people love him. Don't you? You like him? He was a professor here. It's an amazing person. Amazing person that one person can impact the whole society. But politicians said, no, politics one person cannot do. One person cannot do the politics alone and win everything. That's true in reality. But I have no interest, but anyway. Okay. What's a PDF? What's a PDF? probability density function, you stupid, then why keep asking us? Because everything starts from probability density function. Of course, then this will lead into so-called cumulative distribution function. Still going up? A little bit down? Yeah, a little bit. Cumulative distribution function, or simply speaking, you can say CD. Cumulative, keep adding up, that's what that means. Cumulative, they keep adding up. So, cumulative distribution function. And the probability density function I use as a capital X, small x. This is particular outcome out of the random variable x. This is showing the capital letter is random variable, and this CDF is capital Fx. Sometimes I'm using different notation, but who cares? We all know what I intend to do. So you will do something like develop the normal distribution function, then you will develop the data set which could fit. If it doesn't fit the normal distribution function, that's fine, then bring us and we'll taste that data set. Then eventually when you learn the different kind of the probability model, then we'll fit that time, okay? And this is, of course, a probability density function. And what's the area? What's the area of this guy? As one first simple question. If I keep adding, so if I just compute the area under the probability density function, what does it mean? What's the particular value is supposed to have? 1. Everybody feel that? So when you develop your 1 means I'm going to just let's say this is a small x particular value. This is fx, of course, fx x. Then I'm going to from minus infinity, okay? Theoretically, it goes to the negative infinity. For reality, this could be meaningless. Then start from the 0. But mathematically, mathematicians love that, minus infinity. Engineers love to have a finite point, right? It's reality. So minus infinity to the x, fx, x dx, right? If I keep adding up to here, which is equal to the probability such that, PROV, the probability such that x, random variable x, is less than equal to x. That's what that means. What's the probability such that the yield stress is 50 kpsi? Then this is going to be the probability for 50. What's the probability that the yield stress is 100 kpsi? then you expect the value is approaching to what? The probability that yield stress is less than or equal to 1000 kpsi, and this value approach to what? Say 1. Approaching, I didn't say it's 1, okay? Approaching. Because mathematically, it contains the more and more and more area. It's coming down. Coming down means chances to get that value is small. So then what's the probability that the x is between x1 and x2? If you have, of course, a probability density function, that's what you're going to develop. What would be the probability? What would be the probability such that x is between the x1 and x2? What is it? What do you have to do? You have your own the probability model. What do you have to do? You have to compute? Yes, sir? All you have to do is just to compute the area. It's a simple integration problem. Structure reliability is, I could say by the one word, it's a problem, heavy problem to get the integration of the volume under the probability, sort of the probability density function. Volume. Very difficult. So I look at some reliability course that other departments are offering. They don't say detail. There is no first order. The reliability method introduce the detail. We need detail. If you don't know the detail, better not knowing it. If you want to do it and like to know detail, then you have to digging to the topic which is covered very well. Otherwise, you can't use it for next step for your research. Okay, this is 10:57, so I'll see you Friday morning. Okay.